relationship between absorbance and concentration. So let's give it here again. There are limitations to the Beer-Lambert's law. Okay, the first one, the so-called real limitation, tells us that Beer-Lambert's law is applicable only for dilute solutions. Okay, if you're going to plot, okay, again, no, concentration versus absorbance, okay, and if we go to higher concentration levels, what we expect would be something like this. So as you can see, the linear portion, okay, or the linear relationship only exists at a lower concentration. Okay, at higher concentrations, the plot tends to plateau. Okay, now the reason for this is, if you're going to imagine your molecules, no, all right, so you have your molecules here. At the dilute solutions, these molecules are quite far apart. All right. Now, if you remember some depictions of molecules, especially in organic chemistry, you can imagine your molecules to be surrounded by their respective electron clouds. All right. Now, these electron clouds, of course, contains the electrons and the energy levels, no, that we discussed in the previous slide on Jablonski diagrams. Okay, and now since the solution is dilute and the molecules are far apart from each other, their electron clouds do not overlap. Now at higher concentration, this changes, no, because the solution becomes more crowded. Alright, the electron clouds of your molecules will have a chance, no, for overlap. Okay, and this causes a problem, no, in quantitation. Macroscopically, another thing that you can think about is that at higher concentration, especially for colored samples, your samples gets less transmissive, right? Okay, so it gets less transmissive, so more of the radiation is being absorbed because you have more absorbing molecules. Okay, so the tendency is that the since you cannot measure anymore, okay, substantial amounts of transmitted light, so the calculations, no, between transmittance and absorbance becomes call this nagiging parang negligible na, no? So that's why you have this kind of plateau. So normally for UV-vis absorption spectroscopy, acceptable concentrations is 0.1 molar or below, but this actually depends on the absorptivity of the sample. Typically, we want our samples, no, to have absorbances less than 1 AU, no, 1 arbitrary units. Okay, even though instruments, no, UV-vis instruments, for example, can measure up to 4 absorbance units, no. Ano lang yan, no, sa instrument lang talaga yan. Okay, if you get readings that is higher than 1 absorbance units, medyo warning yun, no. So you might want to dilute your sample. I forgot to mention in the previous slide, no, this term here, no, B is your cell path length. All right, basically, so this is in centimeters. The cell path length pertains to the distance, all right, the distance that light travels across the sample. Meaning to say, this is the distance that is filled with your analyte analyte molecules, no? All right, so this is your cell path length, and basically the larger the cell path length, all right, the larger the cell path length, so it means to say that your light encounters more of the analyte molecules, the greater the absorbance becomes. Alright, in case of UV spectroscopy, the cell path length is determined by the diameter of the cuvette. Alright, so later we'll show you different sample holders, no, which dictates the cell path length, no, of your for the Beer-Lambert's law equation. Alright, so this is your real limitation. Okay, so another is your chemical deviation, no? So in Beer-Lambert's law, okay, it's important that your molecule, okay, your analyte does not undergo any changes, no, whether association, dissociation, or reaction with the solvent, okay, that will lead to a product with a different absorbing characteristic, no, compared to your analyte. Okay, so you don't want your analyte molecule to undergo transformations, okay, because, well, basically the manner by which your sample or your analyte absorbs radiation depends fully on its structure. So this is particularly important for ionizable species, no? For example, benzoic acid versus benzoate ion, no? Even though the two molecules are similar, no, but the absorptivity of benzoic acid is different from that of benzoate. Okay, so you have to choose, no, which form you want to measure, and in choosing, what you can do is to control the
Okay, so we
pH
are now on
of
the
your
third
sample.
limitation of
Okay, so
Beer-Lambert's
again,
law.
the analyte should
So
not
the
change
third
its
one
form.
tells us that Beer-Lambert's law is applicable only if monochromatic radiation is used. So when you say monochromatic, it's an electromagnetic radiation with a single wavelength value. Alright? So, well, basically the quantitation via Beer-Lambert's law is only possible if you're using monochromatic radiation. And that's the reason why whenever we do quantitation, we always measure at the so-called lambda max of the molecule. Alright? By the way, no, this is what you call a spectra. Okay, the spectra is a two-dimensional plot between the instrument response, alright, transmittance, absorbance, whatever, versus a function of the energy of radiation, no? So usually it's in wavelength. You can also use frequency or even wave number. Alright, so this is what you call a spectra. Okay, now basically the reason why you need to use monochromatic radiation is that the molar absorptivity is dependent on the wavelength of radiation. Okay, it's dependent on the wavelength of radiation. So if you're exposing your sample, you're measuring the absorbance using polychromatic sources, okay, what you're actually doing there is that you are measuring the absorbance of the molecule at different, no, with different molar absorptivities. And remember, the molar absorptivity is your proportionality constant. Okay, now one reason why we want to measure at the lambda max is because of the limitation of the wavelength selectors, no? So wavelength selectors have this thing, no, which we call your bandwidth. Okay, so this refers to the accuracy, no, by which a wavelength selector filters out polychromatic radiation, okay, to obtain monochromatic radiation. Okay, so normally this bandwidth sets up the limitation no, on the accuracy of your wavelength selector. No, for example, no, typical UV spectrophotometers, okay, are rated, no, based on their monochromators, are rated uh, with bandwidths like 5 nanometers, 1 nanometer, or 0.1 nanometers. Okay, so if you say that the bandwidth of your uh, spectrophotometer is 5 nanometers, if you set the wavelength, no, at 350 nanometers, this is actually plus minus 5 nanometers. No? So as you go down, no, in this listing, you tend to have a more accurate uh, measurement, no, of the wavelength. Now, because of this bandwidth, what happens is this, no? If you're going to measure the absorbance, say here, no, at this point of this, at this particular wavelength, no, far away from the lambda max, okay, since you have uh, this range of wavelengths, what will happen is that you will get this curvature in your Beer-Lambert's law, okay, because you are measuring at a certain range of different wavelengths, okay, and each wavelength will have different absorbance values. But if you measure at the lambda max, alright, even though you have a bandwidth, the absorbances at each discrete wavelength values are near each other. Okay, so nagiging negligible yung error caused by your bandwidth, no? And you get a more linear response. Okay, so measuring at lambda max improves, of course, the accuracy of the absorbance measurement, as well as it also improves the selectivity. Why? Because the lambda max of a given molecule is another qualitative parameter, no, for that molecule. So not many molecules would have the same lambda max value. Okay, so that is for instrumental deviation with polychromatic deviation. And then lastly, you have the instrumental deviation due to the presence of stray radiation. So stray radiation results from scattering phenomena, no, in the optical components of your spectrophotometer. Okay, so what happens is that the the stray radiation could differ greatly in wavelength from the principal radiation and may not have passed through the sample nor the solvent. So in theory, sabi ni Beer-Lambert's law, lahat ng ilaw galing dun sa light source wherein the intensity or power of this incident radiation measured by the instrument also all of it passes through the sample, no, and then you measure the transmitted radiation. However, if you have stray radiation, no, meaning to say the incident beam, no, not all of it passes through the sample. Some of it are reflected, deflected, scattered. All right. So the attenuation or the lowering ng energy or intensity or power ng incident radiation is not all due to absorbance, no? So merong competing unmeasured variable, okay, that causes the decrease in the energy or intensity of the transmitted light, no? So this will cause errors, okay. This is one of the reason why when you measure using cuvettes, no, you only fill this up to 3/4 full, okay. So this is to prevent any unnecessary, no, stray radiation, and also that's why we close down, no, the sample compartment cover, no, of course to prevent uh, outside light, no, from interfering, as well as causing unnecessary stray radiation. Okay. Typically, the lesser optical component you have in your instrument, it would be better, no? Because you have lower chances of having this stray radiation. So these are now the four limitations of your Beer-Lambert's law. Okay, so luminescence, so kanina, absorbance yung pag-usapan natin. So we are measuring the amount of radiation absorbed by your sample, no? Something that a sample that can absorb radiation. Now another way, no, that you can use uh, spectroscopic properties, no, for instrumental analysis by measuring luminescence. So luminescence, we talk about the measurement of the emitted radiation, no, of your analyte, okay, after being exposed to a light source, no. So there are a number of analytes, no, that can undergo radiative relaxation, okay. So you could term that luminescence, okay. So when you measure the intensity, okay, so this not follows anymore Beer-Lambert's law, but interestingly, the intensity of the emitted radiation is directly proportional still, no, to your concentration, no? And again related by a proportionality constant. So meaning to say, computationally, pag magko-compute tayo and using fluorescence, if the treatment is the same as with absorbance spectroscopy, no? So if you make calibration curves, slope, y-intercept, etc., okay, you can still use the techniques that we've learned from absorbance measurements. No, just take note that the instrument response now is the intensity of the radiation, no, whether fluorescence intensity or phosphorescence intensity. Okay. Now, luminescence is the term they like to use for uh, sample analytes, no, that undergo or that emit radiation upon exposure to a radiative source. So may light source, no, for you to undergo fluorescence or phosphorescence. But if you want to, or if you're using the term emission, this refers to a radiative process wherein the excitation is not caused by a light source, but rather the excitation is caused by flame, plasma, or electricity. And this actually covers your atomic emission spectroscopy. So in atomic emission spectroscopy, you have their atomic flame emission, you have there your plasma, yung inductively coupled plasma spectroscopy. So there, the atoms are excited because of the heat or the energy of the plasma or their flame, okay, which upon relaxation causes the emission of radiation, no? Or you can even use electricity, such as that for arc or spark methods. Okay. So for luminescence, no, again fluorescence is short-lived, no, few seconds, no, less than 1 second, few milliseconds. Okay, and for you to measure fluorescence, you need to have a continuous source of radiation, no. So kailangan iniilawan pa rin yung sample, no, para continuously produce ng fluorescence. In contrast, phosphorescence, sabi natin kanina, no, it has a greater lifetime, no, and the emission of light continues even after the cessation of irradiation, no? After mo patayin yung ilaw or i-block mo yung light source, the sample that undergoes phosphorescence will continue to produce radiation. Okay. Now for luminescence, no, fluorescence, phosphorescence, two spectra can be obtained. No, the first one refers to the excitation spectra, okay, the absorption spectra, no, and the other one is what we call the emission spectra. No? So there are two
characteristic spectra, no? And this has a consequence, of course, in the instrumentation, no, for luminescence instruments. For the self-assessment for this module, I'm going to upload it as a PDF file na lang, no, dun sa FB group natin. So paki-download na lang. And again, the answers, I'll post it again once I finish uploading yung susunod na module.